with RASM. And should I still ask to repeat the question? Do we have? That's fine today. Okay. All right, take it away, Sami.
So I'm, as mentioned, Sami Kamal, and I'll be part of Team RASM. And I can't believe that's the first picture of a polar bear in an Arctic workshop. So this is a mother polar bear with her cub. They were swimming to ice in the wrong direction. That was 2017, so I know where the right direction was. If that was 2016, I wouldn't have known. So you have seen this slide in the last presentation. That's basically the wiring diagram for RASM and the domains. For the forecast purposes, it's important to know that WRF and VIC are running on 50 kilometers on the extended ocean domain, and the SAIS and PAP are running in 9 kilometers. That's at least the configurations I used for the forecast, and it's in the central Arctic domain, and that's where I take the forecast. There's a wiring diagram here. This is atmosphere, VIC and RVIC, and the coupler talking to each other. The forcing, the RASM is a regional model, which means that our domain does not extend to the whole globe. We need boundary conditions and initial conditions to run the model. And the initial conditions we generate, the boundary conditions are reanalysis based or CFS v2 based for forecast ensembles, and they are prescribed on the edges of the atmospheric domain. And the atmospheric domain talk to all of that, and then we get the output at the sea ice domain. So the goal is to tell the polar bears where to swim or gain predictive understanding of Arctic climate as it's moving towards seasonably ice-free. RASM has been used to hindcast detailed climate. So we use reanalysis, old reanalysis, and we get force the model with, and we get detailed image of the Arctic climate, including high-resolution sea ice output. And in 2016, it was used for the first time to produce forecast as a part of the SIPN effort. And we used RASM 109. It was an old version of RASM. As mentioned by Winslow, it included WRF 3.2, size 4. I have two big fingers. And POP 2. We had one ensemble member for June, one ensemble member for July, and 6 for August. I was learning. And we did have statistical error correction of about 3 million square kilometers, and the residuals after the statistical error corrections were about plus or minus 500,000 square kilometer. For 2017, we repeated the same thing, slightly modified. We used RASM 1015, which include WRF 3.7 and size 5, and it includes GRIL 3D cumulus parameterization with shallow cumulus turned on over the ocean. We had 12 ensemble members for June, including 3 root cases, July, and 28 for August. And we did not need statistical error correction because we thought our residual was already in the 500,000 square kilometer, and the value looked way more reasonable than 2016, which is about 8 million. Initial conditions for RASM are generated from long runs from 1997 to the present using CFSR, forced with CFSR on the edges of the atmospheric domain, and nudging temperature and wind above 500 millibar. So we generate the forecast ensemble by switching the forcing from CFSR to CFS v2. We use 7 CFS v2 data, initialized a day apart in the last 7 days of the months before the initialization months. That will become clear in the next slide. So let's dive in. That's basically an image of a table of all the work I've done in the last 2 months, 2 or 3 months. It includes all the results of all the runs for 2016. In the top here, you see the target months, which is the months we're forecasting. The output for this month is monthly mean. So when we're looking at the target months, it's monthly mean. Here, you see the initial conditions error. All of the cases initialized from January, February, March to October. And the least error was in September, 8.310 to 3. And the highest error was in August. In all initial conditions, we're underestimating. Error here is observations minus, model minus observation, sorry. So we are underestimating in all initial conditions in terms of error. But when we look at our forecast error, it actually goes up and down. So here you have the target months, February, for lead time equal 1 month. Lead time is the difference between the initialization months and the target months. So lead time here is 1 month, even though the model actually ran for 2 months. I'm not going to mention that again. And we have all the months. So this is February, target months, lead time equal 1 month. It means it was initialized in January. March, lead time equal 1 month. It means it was initialized in February, and so forth. If we look at September, the last one here, that's equivalent to SIPN forecast, and that's basically what we model our experiment on here. So this is SIPN forecast from June, that's 3 months lead time. SIPN forecast from July, lead time of 2 months, and August, that's 1 month. Again, our best initial conditions were for September, and our worst were for August. And I'll go over each one of these lead times in detail in the next slide. So this is the model error for lead time equal 1 month. On the x-axis is the target months. On the y-axis is meter squared, so it's multiplied by 12, so this million square kilometers. And our error here ranges from minus 0.5 to 4 million square kilometers. And remember, our initial conditions error were always negative. The model forced with CFSR was always underestimated ice. Underestimated ice. But once we ran the forecast, we get everything from negative to positive and gradient in between. The error bars are standard deviation of the 7 ensemble members. So I forgot to mention that. Every target month, every initialization, we had 7 ensemble members. So that is the standard deviation of the 7 ensemble members. And we use that as a proxy for the spread, even though 7 is not really a large number of ensemble members. So here I will show the worst and the best cases for 1 month lead time. The best case in terms of extent was the August case initialized from July. And that is the CI's concentration, CI thickness. That will be the same for the few next slides. So on top will be concentration, thickness, minimum error in the left, maximum error in the right. So this 1 month lead time, June means it's initialized in May. 1 month lead time, August means it initialized in July. The IC error for initial condition error for both of these cases were small, comparable to each other, and negative. But once we run the simulation, our minimum error is very small here, 10 to 9, and our maximum error is 0.3 million square kilometer. And again, this is positive. So we started with underestimating by about 500,000, and we end up overestimating by about 1/3 In pink is the observations, black is the model extent. Extent here is defined as area larger than, with concentration larger than 15%, at or larger than 15%. And it's kind of funny, even though this case has low error, relatively low error, you can see that actually the extent, the sea ice concentration map doesn't look that skillful because we have a shifted pattern. We have some positive bias here and negative bias here, and that cancels each other in the extent. I would argue that this actually looks better. So that's 1 month lead time, that's 2 months lead time, and as usual, you will find this feature. June will always be a local maxima in error. It was a absolute maxima in error in the 1 month lead time, but in the 2 months lead time, it actually was negative before, negative after, and got positive and very divergent in terms of the forecast ensemble. So here again, that is the worst time. The worst forecast was October forecast from August, and the best forecast was November forecast from September. Initial conditions error here, both were negative. As a matter of fact, that's decently large error. That's 0.7 million square kilometers. And our error in both forecasts is positive. This is very small, less than 0.04 of million square kilometers. And here it's about 500,000 square kilometers. Again, that's sea ice concentration, and that's thickness of the forecast. And we're forecasting November here, and we're forecasting October. So that is the result for lead time equals 3 months. As usual, June will be a very high peak. We have decent skill in May, kind of horrible skill in the wrong direction in July, but June, for some reason, still a peak, and the spread in September and October seems to be the largest. So we'll look at the best case and the worst case for this forecast. The best case was August forecast from May. So the IC error was 500,000, and our forecast error was a lot less than that. Thank you. And for this case, October forecast, our initial condition errors, which was from July, where 3 months lead time, is 500,000, and our error is also 0.6 million. So that's lead time equal 4 months, and the best case is, so that is beyond what I mentioned before. That's lead time beyond the SIPN time scale. It's 4 months and 5 months, so we're now forecasting September 2017 from May. And surprisingly, that is the most accurate September forecast for the whole year. So our error was like 0.03 million square kilometer. We forecasted 4.77, and observation was like about 4.8. And that's the sea ice concentration, sea ice thickness here. This is the initial conditions. And the error in the initial conditions was order of magnitude larger than the error in the target months, which was September. The next slide, we're even forecasting September, that should have been 5 months. That's a mistake. So lead time 5 months, but the model ran for 6. And that's the initial conditions from April, and you can see the model and observations. Error in initial conditions, about 500,000 as well, underestimating. Error in September is slightly larger. We forecasted less than the observation, and it's also negative, so it's 2.5, 2.7, 10 to 11 million square kilometers. So summary of the talk, we have consistently used RASM to forecast every month of 2017 with lead time from 1 month to 3 months. We also forecasted September with lead time of 4 and 5 months. We had 7 ensemble members, and each one of them ran for 6 months from initialization date, forced with CFS V2 for lead time equal 1 month. Our August forecast was the most accurate, and our June forecast was the least accurate for lead time equal 2 months. November's forecast was the most accurate. October was the least. For lead time equal 3 months, August was the most accurate, and October was the least accurate. So current and future work, that's actually, the experiment was a proof of concept. We ran that, it was a lot of work, and then we realized there is a lot of caveats, and there is a lot of room to improve. For example, we need to include daily ice. I'm in the wrong direction. We need to include daily sea ice forecast analysis, because this jump in June, I doubt that nature changed its mind from negative to positive to negative in 1 month. There's definitely a curve there, and we would need to know what is that related to, why we have less skill in June usually, or June, July-ish. We need to increase the number of forecast ensemble. If I learned one thing from the few talks ahead of me is larger ensemble usually means good. We need to study the variability of RASM compared to itself, so we need to run some ideal model experiments with RASM, and we need to do something similar with the forcing data being CFSR and CFS V2. We need to analyze the scale of these models and the variability in them so that we know where is the error in our target month forecast is coming from, because our initial conditions are relatively more accurate. We looked at 1 year and we looked at monthly, and I suggested look at daily. The other side of the time spectrum, we need to look at interannual and decadal variability. 1 year is not going to tell us much. We need to increase model resolution. We're already working on that, and we'll mention some results for that. And the other thing is diversify the sources of hindcast and specifically forecasts. So if you have any data set that's comparable to CFS V2, that we can use to force our model, please talk to me. And thank you, but I'm going to mention something quickly. That slide Winslow showed, that's actually ensemble mean. That was September 2018 forecast with 6 months lead time from April. That's an ensemble mean of 7 cases. I didn't cherry pick. Some of the cases give us lower numbers than that, but I just took the ensemble mean. So that's just the last point I say. Thank you.
Thanks, Sami. And we have a couple minutes for questions. I have a question. So this system, you are going to keep making year-round forecasts?
Hopefully, yeah.
Okay, well, we'd love to have your data in the new SIPIN2 portal.
So all the SIPIN starting soon. So.
Yeah, with the call for the June call coming up this week. Any other questions? Yep, Bill. Do we have a...
With the river routing, and wondering, that's a very nice way to treat the... having the continental river routing is a very nice way to treat the river inputs. And have you assessed the impact on the salinity distribution and how realistic it is? And
Not yet. These results are like 2 weeks old, some of them, so yes. I haven't still done the analysis. There is a ton of analysis to be done, and salinity is one of them. And we have colleagues working on the fluxes right now.
Yeah, it would be interesting to compare the river flow volumes to sort of observed values.
So, absolutely.
We have Wisla.
Still me here. I wanted to reply to Bill's question. For that particular simulation, we haven't, but we have a paper on the impact of routing scheme in the coastal ocean and the surface ocean in the Arctic. The impact is significant. Change in salinity by RVIC between 2 simulations, one with and one without a routing scheme, can change your surface salinity in most of the coastal regions in the Arctic by 2-3 parts per million. Sorry. So we have looked at that, and there's a paper. If you talk to me later, I can provide the reference.
Right. Any other questions? All right. Well, thanks, Sami. And next we have Michael Sigmund, who was going to talk to us about some metrics we haven't talked too much about yet, and seasonal forecast of retreat and advanced dates.
Where's the edge? Thanks, Ed. So yes, I'm going to talk about seasonal forecast of retreat dates, also known as ice-free dates or melt dates, and advanced dates, also known as freeze-up dates. So in CANSIPSYS, which is our dynamical seasonal forecast system, so we've been developing these experimental forecasts for the last few years, and I'm very happy to present today our first new real-time forecast. But before doing that, I really have to obey one of the 10 commandments at CCCMA, which is thou shalt not present a forecast without an estimate of how skillful the forecast might be, or how useful the forecast might be. So I'm going to revisit some of our work that we published in 2016. It's actually just a year old now, a year and a half. So I'm going to show how skillful our forecasts are for the advance and the retreat date predictions. What are the sources? But then I'm going to show some exciting new developments, some improvements in our new system and our forecast for 2018. I don't have to show this in detail. Bill already showed this. CANSIPSYS is based on two GCMs, CanCM 3 and 4. They have the same ocean and sea ice, just different atmospheres. We run 10 and some more members for each GCM, so 20 in total. 12-month forecast range. We have hindcasts initialized every first of the month over this time period. We use a very simple coarse resolution sea ice model, as Bill mentioned. We initialize in our current system sea ice concentration with head ISST 1.1 and sea ice thickness with a climatology. As Bill mentioned, both of these choices seemed reasonable at the time that CanCIPS was developed, but they had some pretty significant drawbacks, as we'll see later. So how am I going to quantify the forecast scale of retreat dates? Now, first I'm going to define what a retreat date is. It's the first calendar day with sea ice concentration dropping below 50%. We played with different thresholds and we got roughly similar results. And it should stay below 50% for at least 10 days. So you need daily sea ice concentration for this kind of analysis. And also another constraint is that it should fall in this time period between April 1st and October 1st. And then I'm going to consider the forecast scale of this particular date for forecasts that were initialized within the retreat season, so June 1st, May 1st, April 1st, but also in all these model hindcasts that were initialized before the season, this retreat season. Same for the advance dates. It's the inverse of the retreat dates. I'm going to consider all the hindcasts that were initialized in the advanced date, or the advanced season, December 1st, and then all the way back to January 1st. The scale metric that we've used is the anomaly correlation, which is statistically significant when it exceeds 0.3 for our sample size of 32 years. And I'm going to say that our forecast is skillful when the anomaly correlation exceeds 0.3. And also, I'm only going to consider grid points where the retreat or the advanced date has been defined in more than 75% of the historical data set. So you see some areas where it's white, and it means that you don't have enough data points to have or assess the scale, basically. Okay, so first, climatology. Our model does a fairly decent job in simulating the observed retreat date. Climatology, so it starts to melt in the Sea of Okhotsk in April, Bering Strait, then it reaches June, and that's in Spain in June, and then later in the season near the Arctic Ocean. And again, this white means that there's not, or it's not retreating in at all over the historical period, actually. Okay, so for the advanced states, we have a little bit of a bias. We are a bit 3 weeks later or so. But generally, these biases can be accounted for by a simple bias correction. And it generally doesn't affect the scale except for the Bering Sea here, where we basically our model simulates too little sea ice or no sea ice at all. So you'll see that our freeze update forecasts are really affected by that. Okay, so the anomaly correlation, the forecast scale now. This is for the retreat date, or the ice-free date. When we initialize May 1st, which is well in the retreat season, we get significant scale indicated by these red colors in most of the Arctic, except the Beaufort Sea, the Chukchi Sea. So what happens if you initialize our model earlier in the season? Well, I can show you this plot for all these 12 months, but I'm not going to do that. I'm going to condense information by showing you the earliest initialization month where we can get a significant skill of the retreat date. With the additional constraint that the forecast remains skillful if you initialize closer to the retreat date. So this is shown in this plot, and it basically shows, for example, for the Hudson's Bay, that May 1st, so that this initialization date that I showed here, is the earliest that you can get a skillful prediction of the retreat date, which occurs January, like late June, early July. Another way of summarizing it is the maximum lack of significant skill, which is basically the difference between this between the climatological retreat date and the earliest date with significant skill, which on average is about 3 months over the Arctic. For the advanced stage, we get generally higher skill, except, as I said, in the Bering Sea over here. And then the maximum lack of significant skill is about 5 months. So what are the sources of the skill? Well, there's basically 3 sources of the skill. First, it's not really a source, but it's a trend. It's related to the initialization. If you initialize with the right trend, you get the trend back. So it's shown by this plot. So this is the maximum lead time of significant skill for the retreat dates with the trend. If you detrend the observations and detrend the model, and then redo this calculation, you get this plot. The skill drops, or the maximum lead time of skill drops to 2.2 months on average. And for the advanced state, this drop in skill is even larger. So for detrended advanced states, we have skill approximately on average 3.3 months in advance. But of note is that even after detrending, the advanced state skill is larger than for the retreat dates. And that's consistent with previous findings that the winter sea ice edge is more predictable than in summer. Okay, so another source of skill is persistence. So this on the right here is shown basically the maximum lead time of significant skill based on a statistical model. It's basically anomaly persistence. You persist your sea ice concentration anomaly, calculate the forecast or the retreat date, and then you calculate this metric, and you get a maximum lead time of 1.9 months on average, which is a little bit less than what we get in the model. So our model, for the additional value of our model relative to persistence is relatively modest. It's still higher than this persistence forecast, which is a good thing, but it's not very dramatic. However, for the advanced state predictions, it's a completely different story. There's basically no skill from the advanced or from persistence in advanced state predictions, and that makes sense because prior to freezing up, prior to the advanced state, there's no sea ice, so there's no anomaly to persist. So basically, you end up with a climatological forecast, which in terms of anomaly correlation does not carry any skill. I will skip the third source of re-emergence. Well, I'm going to just briefly mention it. What we actually get, this forecast skill of the advanced state is related to this re-emergence mechanism, and for details I will refer you to our paper. So improvements in the new system. And this is basically a slide summarizing Bill's talk. In the old system, we had this temporal inconsistency between the hindcast and the forecast, which is made our seasonal forecast of sea ice basically unusable. This has been improved by using a new data set that's more consistent with the operational data set used to initialize our operational forecast. So this is really a game changer for us, because now we actually have usable forecasts of sea ice. And also we increased, or we made some other improvements related to sea ice thickness initialization and subsurface ocean temperature initialization. Basically, this increases the temporal consistency between the hindcast and the forecast. And I think it has, this new product that we're using has a better trend as well. Anyways, so this is the improvements we made in the hindcast and forecast that's being considered for operations. And so how does it affect the retreat date skills? Well, this is again for May 1st initialization. Just to compare the two, you get generally increased skill. We get significant skill now in in Beaufort Sea as well. The maximum lag with significant skill increases quite dramatically from 2.5 to 3.6 months. For the advanced dates, well, in November we already had very high skill, but the maximum lag with significant skill actually increases from about 5 to 7 months, which is quite dramatic. I should say that most of this skill improvement in the new system comes from a better representation of the trend. So for the detrended advance and retreat dates, the improvement is about 10% or so. So it's not as dramatic as for the full anomalies. Okay, our forecast for 2018. So these are all defined in terms of anomalies relative to this 2009 to 2017 climatology. It's for the retreat and advanced stages, focusing on our contribution to the consensus forecast. In Baffin Bay, we generally have ice. It's generally ice-free in September. So our forecast will be based on these retreat and advanced dates. And we'll show that for our May 1st forecast, we predict basically blue colors here means a shorter open water season, so a later retreat date and an early advanced date. So we see that blue colors in both plots. So it means that we predict extremely high sea ice conditions for the Baffin Bay for this season. Confidence somewhat uncertain. This is the forecast scale for May initialization. It's significant for the retreat date, but it's not yet quite significant for the advanced stage. If we wait a few weeks and we initialize on June 1st, we will expect some skill for the advanced date. So, our June 1st forecast might be a bit more skillful. The Northern Sea route accessibility, well, it's really mixed with mostly warm colors in the Kara Sea, but cold colors in the Laptev Sea. So there's more ice in the Laptev Sea, or a later retreat, later melt date. Confidence is quite uncertain. There's some skill in the Kara Sea, but not much in the Eastern Siberia and the Laptev Seas. Or where these white colors are is that we just don't have enough data in the past to come up with a a skill estimate. Northwest Passage, low sea ice in general, but there's also these blue colors here, and yeah, the skill is not very impressive, I should say. And so all these anomalies were relative to 2009 to 2017, which makes our job a bit more challenging if you just plot the anomalies relative to this long-term climatology. Well, you get a lot of skill from the trend, and we see that basically everywhere we see shorter open water seasons or longer open water seasons than this climatological average. Okay, so conclusions. We have skill for seasonal forecasts of advance and retreat dates. Advance dates are more predictable than retreat dates. We have improved sea ice concentration and thickness initialization. The improved sea ice concentration initialization allows for usable real-time forecast, which is really a game changer. And then improved initialization substantially improves skill of advance and retreat dates. And I just mentioned that all this coding has been in Python, and we intend to make it freely available. So if you're interested in that, come and see me. So thanks for your attention.
Thanks, Michael. We have a couple minutes for questions. And we have Bruno.
In Nain, Labrador this year, like the ice came late, and they expected to go away like earlier, and you seem to be showing that too, like a reversal between the blue color and the red color, like between Baffin Bay and Labrador. Can you explain how can you have like this reversal in color there? Like in the next slide.
But, I think I missed it. It's basically because of the large trends in the historical time period. So if you plot it relative to this time period, you get a different anomaly than if you plot it relative to 2009 to 2017. Different reference period.
I have a quick question. So this asymmetry you see in skill between the advance and retreat, how much do you think that's due to having the right sea ice thickness in the retreat season, right? So if you're predicting in April or May, the next season, and you think about that sea ice edge moving north, you kind of probably, those sea ice thickness anomalies are going to be quite critical for that prediction. So how much? But I noticed your new system does assimilate or use sea ice thickness information, but didn't seem to improve too much.
Yes, so in our old system, there's nothing from that.
Right.
In our new system, we do see increased skill on average. So there must be some of that.
But it's still quite a bit less than the advance prediction.
Yes.
Okay.
Yeah, correct. Yeah, so it's really the advance that dates that benefit from the slower timescales in the ocean. That's really the main source of predictability.
Right. Thanks. Any more burning questions before we welcome David Herbert to close our session? So we have a last talk before lunch. David with a subseasonal polar forecasting with the US Navy model, NESM.
All right, Ron, ready to go. Okay, so I'm David Heberts, and I'll be giving you an overview of our subseasonal forecasting with this system we're developing called the Navy Earth System Model, NESM. This is work, a lot of this work's been done with Joe and Neil Barton, along with the rest of our collaborators here from Stennis. And other than Neil, Neil's at Monterey, but all with the Naval Research Lab. So I'll give you an overview of our model here. We'll talk about what our major statistic that we use is ice edge error. Our contributions to sea ice outlook from last year, and then what we've done with SIDFEX. Okay, here's the obligatory wiring diagram. So here's our Navy Earth System model. So we have our ice code is SICE, HICOM is our ocean, NAVGEM is our atmosphere, and then we have waves with WaveWatch 3. We notice the arrows, all of this goes into a mediator, so then it gets coupled to everywhere. At this point, you'll see that's only really one-way couple going to the wave model. We don't have wave data coming in, say, to our ocean model just yet, or our ice model. What we can do, though, is say in the absence of a coupled model, we can put in like data forcing instead. So for example, our current operational system is not coupled with the atmosphere. It's directly forced with NAVGEM. So in this case, that the NAVGEM would be a data atmosphere going into that couple, or going into that mediator, then to force the ocean and ice. And so here's just another more details in our system. So currently this system's going to be run in two different ways, in a deterministic mode and a ensemble forecast mode. And so the deterministic, the goal is to be between 0 and 16-day forecast. The atmosphere model will be at 19 kilometers. Ocean will be at 125th degree. SICE model will be same grid as the ocean, 125th degree. And then wave model will be 1/8 degree. Probabilistic will be a little less on the resolution just because of the time it takes to run it. So pretty much the deterministic is half the resolution of, the ensemble is half the resolution of the deterministic. And what I'll point out here is we have, at this state, we're looking at this initial operational capability here, which will occur next fiscal year for us, so starting sometime after September, so fiscal year 19. And our SICE code is version 4. And then our final operating capability is going to be in fiscal year 22 is the plan, and we'll have upgraded then to the SICE code version 5. Or by then maybe 6, we'll see. But one thing I want to focus now is, I'll be talking about just the probabilistic, what we've been using, because that gives our forecast from 0 to 45 day in terms of subseasonal forecasts. So just the lower resolution forecast system. So ice edge, I want to just briefly discuss what we consider ice edge, just define terms so we're all on the same page. So ice edge, what we do is we get from the NIC every day, the National Ice Center, we get the locations of the ice edge that an analyst locates. And we get those as a series of these black dots. And what we do is we determine the distance between these black dots and what we define as our model ice edge. So what do we define as our model ice edge? We define it as a grid cell that has 5% ice concentration with a neighboring grid cell that's less than 5%. And then, like I said, we do the distance between those two. It's an absolute distance when we report our error statistic. We do have a method internally. We'll say, okay, whether it's over or underestimating. Basically, the way we determine that is if this ice edge spot is inside of a grid cell that has ice, then we've overestimated. And if the black dot's outside of ice, then we've underestimated. That's how we do that. So that's how we're defining our ice edge statistic. And one of the reasons we focus on this is one of our main customers, we send this, our model output to the National Ice Center, and it's used for their analysts for safety of navigation forecasts. So here is a look at our ice edge error. This is done for the Pan-Arctic now for this 45-day forecast. Oh, I guess what I should, okay, what I forgot to tell you here, when we do our ensembles, we do lagged ensembles. So we don't do, say, 5 or 10 ensembles a day. What we do is we do one 45-day forecast every day in a week, and then we'll take a lagged ensemble average for the 45-day forecast based on that weekly runs. And so that's what we have here. So you'll see in this example, we have a 45-day forecast started on this date here, which will be September 23rd, note 24, 25, 26. And then each line corresponds to one of those ensembles. Black line is the average of that. The red line is our current short-term 7-day forecast system, our global ocean forecast system, GOFS. And what the purpose of this is to show is we see that our errors grow kind of linearly within, as we hit, say, a transition point is where we're finding our greatest amount of ice edge error right now. So what we need to try and figure out here is our ensemble long-term forecast just missing that transition from, say, growth to melt or vice versa right now. That's where we stand with this. So moving on to Sea Ice Outlook. So we all know Sea Ice Outlook. We have been contributing to this, I believe last year, 2 years ago I think was the first year we contributed, and I've got last year's results here. So what we would do is something similar. We'll start right for the June. We'll start our simulation in May to get our averages out for the June call for the sea ice extent for September. Same thing, we'll start in June for the July, and then July for August, which is what we see here is from, for the July submission, we were in the middle, which was pretty nice for us anyways, right? So we're pretty happy with that. And still a little under what the average was. And we will continue to contribute this year with Sea Ice Outlook. Just wanted to show everyone where we are in terms of this right now. And then here's a plot from our ensemble of what the mean sea ice extent was from each ensemble. So May, June, July in each column. And then the top row is just the Pan-Arctic, and the bottom is just zoomed in into the Beaufort region here. And of course, the black line is the observations from NASA, from NASA Team 2. Snow and Ice Data Center puts out that ice extent. And I guess the nice thing is, at least in July, we're getting closer to the mean, right? And up here, out here, we are overestimating our extent as for the longer forecast. So again, we're either missing that transition time or just not melting out ice fast enough with our longer lead time forecast right now. Okay. And then so we heard from Axel yesterday about the SIDFEX. We've been contributing to that as well. I guess I won't go into much detail with it other than the green line is our deterministic run starting from either 45-day forecasts, and you can see the dotted lines, solid or dotted, determine whether it was the June, July, or outlook. And we kind of had the same reaction that Axel had. Wow, we're doing pretty surprisingly well, right? So we were surprised that we were getting at least this, on this level of the plot, right? So more investigation, of course. We still want to be better, try and get that average less than 100 kilometers or so for the long-term forecast. But we were at least happy in that state. And that's it. Nice short talk. So here, right, so give you an overview of our Navy Earth system model. It's going to be run in two different ways, a deterministic or ensemble. Our ice edge errors you saw in that model, the animation, they do tend to level off after about 7 days, but we got to work on the transition times with that right now. We did underpredict for the sea ice outlook, but we'll be contributing again this year and continuing with SIDFEX. And that's all I have. Take any questions. Thank you.
Thanks, David, and certainly have some time for questions. Ed?
The outlook pictures you show with the ice edge, was that still based on your 5% threshold? No, the next slide.
Oh, there?
Yeah.
Oh, no, the outlook is 15%. Sorry, we do use 15%. That's standard for everyone else. Yeah. Yeah.
Cool. Okay.
Yeah, I was wondering if your peak in the summer season, whether that might just simply come from the fact that the probability of getting something wrong increases as the ice edge gets longer, because there's, in the beginning you have more ice is still at shore and you have a smaller ice edge, and then you're shrinking the ice pack, you're exposing it, and towards the end you have the smallest, the shortest ice edge. I'm not sure, that might be something to look at.
Yeah, well, sure. I don't have an answer for that, but I will certainly look at it. Yeah. Thank you.
Actually, I had a question about your one of your earlier plots, the slide-in lagged forecasts, and so you said that the red line is your weekly forecast?
So the red line is, right, so our GOFs, right, so our daily. So this will be the daily analysis on each day that are for our I'm going to call pre-operational, what our operational forecast is giving every day. So that's not a weekly average on the red line. That would be our analysis, right? Yeah.
So I just noticed that the times when your when your ensemble forecast, these sort of times when the error increases fairly quickly, it can align with the red one too. Right. So I wonder if that's significant.
Yeah, it's a good question. Yeah, it might be the same mechanism in terms of
that it's something that's hard to predict even in a 1 week forecast, right?
Right. Yeah.
All right.
Yep.
Any other questions? Yep, Cecilia.
Thanks. It's not on. Is it on? Oh yeah, just delayed. This is really neat to see the ice edge error. Is it systematically biased? Is it something you think you might be able to correct? Or have you tried already?
I would say systematically we are under-predicting. How do we correct that? That's a good question.
The last talk of the day may be a useful one to take.
Yeah, and
check out.
quite frankly, I think part of it has to do with, we just haven't done any of those sensitivity studies like Wisla was just talking about. We're using standard default SICE parameters, and we're all about getting as high resolution as we can, so maybe the parameters we're using the default probably aren't as applicable to our 1/12th, 1/25th degree type model. I think that's the place I'd like to start looking for that anyways as well.
Mm-hmm. I think I agree. But
Yeah,
anyway,
thanks.
thank you.
Do we have any more questions? And if not, Bruno, do you have any comments before we close the morning session? It's a 1 hour lunch. Is it going to be as delicious as yesterday? Okay, perfect. All right, see you everyone in an hour. Thanks again to the speakers.